So Pedro, we've got some pretty thick questions, if you will, just sitting in the
Yes.
Q&A right now. Would you, I mean, we'll try to get to them by the end, depending on what we can get through, but if we were to save kind of a transcript of remaining questions that we couldn't get to, would you be okay with just writing up kind of brief responses or something like that? And then we can
Yes.
post those as an additional set of materials online after the
Yes.
webinar is over?
Yes. Okay, we can do
Would
that.
that be okay?
Yes, that's fine. That's fine.
Okay,
Yes, that
okay, we'll
works.
try to get to them, but we just want to make sure that we touch on them at some point. So,
No, perfect. Yes.
okay, all right, thanks. Let's proceed then.
So what I'm gonna do next is like dig into Callaway and Santana procedure, right? So how we tackle these issues with like heterogeneity, how we can avoid this contamination bias and all those things from the very beginning. Like I'm gonna talk about the building blocks and how to do that, right? But in practice, I mean, the implementation of everything I'm gonna talk in the next 40 minutes, it's very easy in terms of software because we have packages in R, the DID package to do that. We have packages in Stata to do that, the CSDID. We also have implementation in Python. It's the differences package, right? Thanks to Bernardo, who have implemented this, right? So, I mean, in terms of practicality, it is not so complicated to use these tools. But what I want is that you guys, when you use it, you understand it from the basics, the building blocks. So that's what I'm going to focus in a minute. Then at the end, we're going to come to the empirical applications. I'm going to show you, right? Go through all this ACA exercise on how to do this in practice. So as I said, we're going to split this task, this complicated problem, into smaller tasks. They are easy to digest. The first task is about identification. And what do I mean by that? When I talk about identification, what I want you to think is like, well, let's abstract away from sample size limitations. Say, I'm going to dream that I have a lot of data. So much data that I'm not even going to bother with that, right? In that world, in which I have all the data I can dream of, like, what is the building block of my analysis, right? So what kind of questions I would like to answer? In the 2x2 setup, right, we settle for the ATT, so the average treatment effect in post-treatment period among treated units. Now, in a situation that I have variation treatment timing, right, and I have several groups in several time periods, a natural starting point is to like extend the ATT to a family of parameters. We're going to call this family of parameters these ATTGTs, which is the average treatment effect among units first treated in period G, and we want to know this average treatment effect in calendar time T. So it's like among units who are first treated in period 10, what's the average treatment effect in period 12, right? So this is like a cohort-specific and time-specific treatment effect. We want to know this effect for several time periods and for several groups. And of course, we're going to retain our focus on all post-treatment time periods. Why are we focusing on post-treatment time periods? Why are we focused on T being after treatment starting date? Because we're going to make an anticipation assumption in a second, and meaning that like before treatment takes place, there is no treatment effect. Right? So treatment effect is only defined after treatment started. So that's our focus on T being post-treatment period. So little t being greater than or equal to little g. So this is like, again, for units who are treated for the first time period G, we do observe YG, right? We do observe the treated potential outcome in period G because that's SUTVA. That's our switching equation structure. The name of the game we're going to be playing is the same game as we played before in the 2x2 case, in which we are trying to impute the outcome, the untreated potential outcome in period T for the group who is actually exposed to treatment for the first time in period little g. So this is the component here that we're going to be like trying to uncover to impute in this analysis. So how are we going to impute this? Again, no magic. Everything comes with assumptions. And the first assumption, because we're leveraging time as a source of variation in our identification strategy, we're going to impose this non-anticipation assumption, meaning that units do not act on the knowledge of the future treatment date before treatment starts. So in all pre-treatment periods, units act as if they are untreated, right? So this essentially impose zero treatment effect before treatment takes place, and but it does not restrict treatment effect dynamics once treatment starts. This is not without a lot of generality. Again, right? This is like, if you have anticipation behavior, you're going to have to relabel what is treatment date, and our packages, both in Stata, in R, and in Python, the Callaway and Santana, allows for some form of violation of the non-anticipation, as long as we know how many units, how many periods you anticipate the treatment. But for the sake of the argument, we're going to abstract away from this for the moment to make things clean. So we are maintaining SUTVA behind the scenes. We are making a non-anticipation assumption. Now, what is the third component for diff and diff? The third component, it has to be some parallel trends. Because remember, guys, what I told you early on. In my view, what defines a difference and differences like analysis, it is we are making some types of parallel trend assumption. Here, there are very many parallel trend assumptions you can make. I'm only going to discuss two of them. That for me is the two easiest of them that you can build on. The first parallel trend, it is a parallel trend based on a never treated group, serving as a comparison group for everybody. And this assumption states that for every time period in every cohort, as long as I am in the post-treatment period, right, we're going to assume that in post-treatment periods, the average evolution of the untreated outcome among cohort G, it is the same as the average evolution of the outcome among the untreated cohort. See here, it's a never treated cohort. It's a special notation if G is equals to infinity. Right, so this is essentially a never treated cohort. So what I'm doing here is like I'm assuming that I have this set of units who remains untreated in every time period, and I'm willing to use these units as a valid counterfactual group for everybody who is eventually treated. You look at me, say, Pedro, what? Two questions. First, what if I do not have a set of never treated units? How do I move? Well, if you do not have a never treated units, this procedure is not really, you cannot, you can make the assumption, but it's not going to give you anywhere. So that's the first drawback. So, well, what about if I have some of them, right? But they're fairly small. Well, we may be losing too much money on the table in terms of statistical power, right? So, third of them, Pedro, never treated units are potentially very different from eventually treated units. I'm not willing to assume parallel trends only among never treated, right? Because if everybody is eventually treated, perhaps there is a two-step process. First, I'm going to decide to be treated. Once I decide to be treated, I'm going to like decide the timing of the treatment. And I don't want to like use those who are never treated as a valid comparison group for those who are eventually treated, because it's kind of like complicating this discussion. And I understand that. And in many applications, this can be true. So in situations when you're not willing to use or not capable of using, because there's no such a data about leveraging parallel trends among never treated units, you can use the next more natural group, which is all units as a control group, which comes to this alternative parallel trend assumption. This is an alternative, right? Which states that for every time period, right, for every group, I want to assume that parallel trends, the average evolution of the untreated potential outcome for the cohort G, it is on average the same as the average evolution of the untreated outcomes among units who have not yet been exposed to treatment. So this DS here is like, I can use any set of units who have not yet been treated in period S, period S is always greater than today, right? So I'm willing to use all eventually treated, I'm willing to use all not yet treated units as a comparison group for me. So that's the idea, is an alternative assumption, right? Oh, of course, this nests the previous assumption on never treated. If you do not want to use the never treated units in your control group, what you should do, you should drop them for your analysis, for your data set, and then you're going to use the not yet, but eventually treated units, right? So these are essentially the issues. Oh, Pedro, but are there trade-offs between these two assumptions? Yes, they are trade-offs about these two assumptions, right? In general, parallel trend assumptions involving the not yet treated units does not restrict only post-treatment periods. It also restricts some pre-treatment periods. This means that this assumption here, it is testable, right? So this whole conversation that parallel trends are never testable, you can only test pre-trends, that is not necessarily true when you are in this world with staggered treatment adoption, because this assumption here, it is directly testable, right? It leads to an over-identification set of restrictions. We can test this. I discussed this in a paper with Michelle Marcus in January, right, which have a lot of details on how you can test this. So these are the two assumptions, types of parallel trend assumptions you can make, but in practice, you're going to have to pick one of them, right? So if you pick the first one, the never treated, Callaway and Santana shows that we can actually identify this ATTGT family of parameters by mapping everything back to the 2x2 case. How is that possible? So in order to identify this ATTGT using the never treated units, we're going to map everything back to the 2x2 situation. How so? First, let's look at the time periods. If I care about average treatment effect in period T, I'm going to keep data from units in time period T. And the only other time period I'm going to keep in my data is the time period G-1. Why G-1? Because this is the latest period before treatment started. So this brings me back to the two period case. I have period post T, period pre G-1. It's the first component, check. What about groups? We also going to have only two groups now. We're going to have cohort G, that's the cohort that I care about, right, in this ATTGT, and the never treated cohort. Again, two groups only. Every single observation that is not from time period T or from time period G-1, and not from period or cohort G or cohort never treated, I'm going to drop them because they're not useful for me under these assumptions, right? Once I have established this identification, I'm back to the 2x2 case, so I can leverage every single thing we talked in the first 2 hours. Because in this subset of data, I can go and compute this guy here by hand if I want to. Make sense? This type of intuition appears, this result appears in Callaway and Santana and in Son and Abraham, right, in very similar time periods. What if you do not want to use the never treated group, but you want to use the not yet treated group as your comparison group? How do you do this? Again, the intuition is very similar, right? We're going to map all this back in the 2 periods case. We're going to use, we care about treatment effect for cohort G, so we're going to keep cohort G into the data set, and also going to keep everybody who has not yet been exposed to treatment by period C in the data set. We care about treatment effect in period C, so we're going to keep period C in the data and period G-1 to serve as a reference group for this guy. Once I have this, again, all this is go back to the 2x2 case, right? We can easily estimate these guys like intuitively. This result appears like in Callaway and Santana, and also in the Charles-Martin and Dufay, right? Though the Charles-Martin and Dufay in the AR paper, they focus only in the case where G and T is exactly the same. So in the AER paper, they focus on the case of instantaneous treatment effects, and they do that because since their paper allows for treatment to turn on and turn off, right? The framework is more complicated, so to do everything in a single shot, they have to rule out dynamics. Callaway and Santana focus on staggered adoption, so because the setup is simpler, we can allow for richer dynamics in that situation. We can also allow for covariates into this analysis, right, to relax part of the trends. In the paper in Callaway and Santana, we discuss this in great detail, right? We can use regression, we can use weighting, we can use double robust methods, we can use machine learning, all that, it's in the paper, right? And I do not have time to cover this in great detail today, right? But all this, we can incorporate covariates to the analysis easily. So one question that I very often get, it is that, Pedro, you must be nuts, right? You're telling me I'm gonna have to drop data all over the place to estimate all this ATTGT. You're not coming from this earth, right? Because as an empirical researcher, we know data is very hard to get. And you're telling you should drop all the data. And I say, wait a minute, I'm telling you you should drop the data to estimate, to identify these ATTGTs, but you do not have to stop there. That's the identification part. Once I have all these pieces of ATTGT, I want you to think about that as Lego pieces. I can give you many Lego pieces. Once I give you the Lego pieces, what are you gonna do next? You can aggregate these Lego pieces into something that is meaningful to you, for you, right? I may want to build a house with my Lego pieces. Like Paul may want to build, I don't know, a car, a hospital. Brady may want to build something else. Each one of us are free to choose how you use our Lego pieces to build things differently. And that's a way to say, like, we can own how we gonna glue all these pieces together, right? And there is no universal way of doing this, like the best way, but there are guided ways of doing this. So generically speaking, how I'm gonna aggregate these families of ATTGTs to a smaller number of parameters? Well, it's gonna come up to being careful about the weights you want to choose, right? And I want to highlight some weights you can choose, right? And they are more like motivation. The motivations for choosing these weights vary depending on the type of heterogeneity I want to highlight, right? And I want to do things in reverse. First, I want to talk about event study aggregation, right? Which is the one I have discussed in the event study to fixed effects regressions and all that. And this is by far the most popular aggregation that I have seen out there. So I'm going to stress only this one. You can look at the other types of aggregation in the slides in your time offline. So if I want to highlight treatment effect heterogeneity with respect to how long has passed since treatment started, and I have this family of ATTGTs, perhaps too many to present them all, I can aggregate these guys together such that everybody that has been exposed to treatment by E periods going to be glued together. What do I mean by that? First, I'm going to relabel things. Instead of writing ATTGT, I'm going to fix T calendar time to vary according to event time. What do I mean by that? This letter E here is going to be an index of how many time periods have passed since treatment started. So when E is equals to 0, it is the treatment effect at the time treatment started. When E equals to 1, it is the average treatment effect 1 period after treatment started. When E equals to 2, 2 periods after treatment started, and so on and so forth. Right? This indicator function here is telling, oh, I'm only going to pick the E's. They're plausible, that they live in my data, and I'm going to average all these ATTs, right, this family of ATTs together, as long as they have the same, I'm going to average across the groups, right? And I'm going to choose weights that are proportional to the group size. So if I have a group who is very large, this group going to have more weights than a group that is very small. Right? So these are the weight. I'm going to call this like population, the group weighted average, right? Which is proportional to the sample size, which is a very reasonable and practical approach on how you're going to average these guys. And this is perhaps the most popular summary measure of treatment effect heterogeneity, like we have seen adopted. And this mimics the event study specification we have covered early on. So this is what I'm telling you. Even though we're deleting the data, splitting all that, we're then gluing them back together in this aggregation step. And then in the paper and in the slides, we have other aggregation schemes as well. But for the interest of time, I'm going to fast forward these aggregation schemes, and you can see this offline. The slides are available to you. And if you have questions, feel free to reach out to me as well. What about estimation and inference? Well, everything that I have shown you here, let's go back. It is based on population expectations. All I have to do is replace population expectations by sample means. Or I can just, after I filter my data, I can fit this into a two-way fixed effects regression, recover the coefficient, and move ahead. So estimation is very simple. It's just like a loop over different two-way fixed effects regressions, depending on the sample construction you're leveraging. That's how you're going to estimate these things. The aggregation is the same. Yeah. So under fairly simple results, we can establish that for each GT pair, we have consistency and asymptotic normality. We can do pointwise inference based on this asymptotic normality. But me, as an econometrician, I'm not a very big fan of pointwise inference because I'm going to plot a lot of these ATTGTs, and these points are highly dependent on each other. If I plot 20 points and I want to do inference across all 20 points, I'm going to run into this issue of multiple testing, right? So the paper in Callaway and Santana, we say, do not rely on pointwise inference. Let's do something that is robust against multiple testing. And to do that, we're going to do bootstrap, right? Again, the mathematical details of the bootstrap, they're all available in the slides. They're available in the paper, right? I have an algorithm here. But the main intuition is that instead of using 1.96 as your critical value, we're going to inflate this critical value in a data-driven way, such that we're going to count for multiple testing issues. Right? So you control the probability of making a type 1 error across the whole curve, the whole treatment effects curve that you care about. I have the algorithm is here. I'm not going to spend much time on those details. You can look at this. Now, that's essentially the heart of Callaway and Santana. Let's go back to the ACA Medicaid expansion example, right? To see how this actually works in practice, right? Because I want to give you the taste of how to do this in practice. This is the day. I'm going to show you this slide. I'm going to show you first the pictures here. Then I'm going to move to the software so we have everything like concisely. So when you care about the ATTGTs, right? In general, the DID package going to spit out for you one event study regression curve for each group. Remember, I have states who expanded Medicaid in different years. So I have a group who expanded in 2014, a group who expanded in 2015, a group in 2016, a group in 2017, and a group in 2019. I'm doing this here because I want to highlight that you should not trust our output blindly, right? Why is that? Some of these groups are very small. So for example, the group who expanded Medicaid in 2016, I have only like 2 states treated. In 2017, I have 1 treated state only. Remember, everything we have said to rely on these classical inference tools, we have to have several treated groups and several control groups, right? So I have to have like many clusters. And here, their assumption is being clearly violated. So I'm presenting these results to you over here to highlight that you should not blindly trust the output of the regression. Go back to the data construction and check if the assumptions make sense. In this case, the assumptions of having many treated and many untreated clusters do not make much sense. So you should not interpret these plots individually. How are you going to bypass this limitation? We're going to, again, glue all these plots together, right? Such that although I have few treated units in some of these groups and few untreated units in some of these groups, when I glue them together, right, I have several treated and several untreated units. And this is the type of plot that you're going to see in Callaway and Santana, right, where looking at pre-treatment periods, things seems very stable. So there is no reason to believe that parallel trends is not a plausible assumption based on pre-treatment observations. And the dynamics here is very similar to before. Oh, Pedro, what is this red line here? The black line, it is the pointwise confidence intervals, right, using standard inference. The red line, it is this uniform confidence bands. And why uniformity here matters? This is a way that we're going to increase our confidence intervals in such a way that we're going to completely bypass these issues with multiple testing, right? So this is like the Callaway and Santana regression using the Medicaid expansion, right? This is using the never treated. We can repeat exactly the same exercise using the not yet treated as a comparison group, right? And all in all, these results are very similar to those which we have seen in 2A fixed effects, right? So this is 2A fixed effects regression. This is Callaway and Santana. This is Callaway and Santana. So before I go to R to show you how to do all this, let me stress the takeaway messages of all this heterogeneity robust analysis. It is that 2A fixed effects, right, when I have variation treatment time and dynamics, in general, does not respect our assumptions. It doesn't respect like parallel trends in the way we are used to it. It doesn't respect no contamination. It's kind of very aggressive towards minimizing mean square error. We want to be careful with our assumptions. We want our methods to respect our assumptions. One way of doing that is to use estimation techniques, difference and difference procedures that are designed to respect our assumptions from the very beginning. And that's essentially what Callaway and Santana it's all about. You can use the ATTGTs as building blocks. We can glue these building blocks together, right? And once we do that, we don't lose much information, precision, compared to 2A fixed effects, and we gain back this kind of policy relevance because our weights are highly interpretable, right? I want to finish this today, like in the last 10 minutes, to show how you can do all this into the software, right? So to do that, I'm going to switch into R. And meanwhile, if anybody has questions, I'm happy to. I know you have like 26 questions. We're going to have some time to answer some of those. But meanwhile, when I open here, you can feel free to ask them.
Okay, we'll just kind of back up here. And again, we'll save questions that don't get answered in the time allowed today, but try to get through some of these. So if treatment can turn on and off over time, and whether or not the treatment is turned on is likely dependent on time varying covariates, what would be the recommendation for accounting for those covariates?
You're going to have to rely on a conditional parallel trend assumption, right? Essentially, those covariates have to be not affected by treatment. That's the first go. And then you want to allow for like conditional parallel trends type of assumptions. And that's the way to do it.
Got it. Okay. What are the considerations in instances where there are three comparison groups, 2 treatment groups with different treatments and 1 control? Both treatment groups receive the treatment at the same period of time. can we include all three groups in one estimation, or should I make a series of 2x2 DID estimations?
So the way I use, the definition of treatment groups in Callaway and Santana is depending only on treatment timing. Right? So if all of them share the same treatment time, in my word, they're going to belong to the same group. Right? So you can group them together and have a single one. But then you say, oh, Pedro, but I'm interested in heterogeneity within this group. Then you can split them and do one by one. So there is no one size fits all to that type of questions. It's going to depend on what is your interest. Right? If you want a summary at the group level, you put them together and have them together. If you want to break that down for heterogeneity, which is going to provide a richer picture of heterogeneity, you can do this separately.
Got it. Okay. And if you're ready, Pedro, go ahead with your example. Otherwise, I can read some more.
Yeah, I think I'm good to go here.
Okay.
Oops. No, wait. Stop this one. I have too many R things open. So I do have the R file here, which is based on the empirical exercise of the ACA example for the health insurance. In this library, this exercise, I'm going to use some general purpose like libraries. Again, if these libraries, you don't have them installed in your software, go to packages and install them, right? In terms of difference and differences libraries I'm going to use my own library, DID. You can install the most recent version of the library using the GitHub, which lives in GitHub. I'm also going to use the Bacon decomposition library to do the Bacon decomposition weights, and the 2A fixed effects library to do this kind of the French decomposition weights. Right? I'm going to go ahead and load all this together, right? So everything is ready to go. I have some commands for having plots who have transparent background. And I want to highlight this because it took me like several hours to figure out how to map my slides, my plots, to adapt to the background of my slides. And this is the plot that the scheme that I use. If you want to use it, fine. If you don't want to use it, fine as well. It's included in the exercise. So I'm going to load the data, which is the ACA exercise, right? I'm making some transformations to ensure that my data is stored properly to do my analysis in R. I document all these transformations over here. So this should be like easy to follow in your own time. So when I do the 2A fixed effects regression, right, the static regression that we discussed early on in the Bacon before we talk about Bacon decompositions, and we found that the 2A fixed effects regression was the beta hat was 0.074. It's essentially a regression of the outcome of interest, so which is the health insurance rate in a given state, against state fixed effects, which is my unit of observation here, year fixed effects, and I have this treatment dummy, DIT. So fixed effects here enters after this dash, which is the syntax of this FEO, the fixed effects OLS command. And this is, so essentially, when I do this, this variables lives inside the ACFS dataset. I want to have population weights such that bigger states who have more people matter more than smaller states. And I want to cluster my standard errors at the state level, right? I run this regression. I summarize. This is the coefficient we have reported before. And that's essentially like we started all this business of talking about difference and differences and 2A fixed effects in setups which I have variation treatment timing. It was to understand what beta hat was actually doing it. So I do this beta hat here, right? Then I want to know what I want to apply the Bacon decomposition. How do I apply the Bacon decomposition? I'm going to use the Bacon function who lives inside the Bacon decomp library, right? So since I have loaded this library already, I have this library over here. I want to have the outcome of interest. This is my treatment variable. ID variable is my state fixed effects. Time variable is my time fixed effects. I want to run this guys here. In R, it doesn't allow for weights. So I'm going to do the Bacon decomposition without weights, right? and this is essentially the weights. This is the modification of the weights reported in the slides. They differ from the slides because in the slide I have weights, right? Here I do not have weights, so that's essentially the differences. So the treated versus untreated, the coefficient is 0.07, weights around 80%, right? Later treated versus early treated, this is the forbidden comparison, right? Which has around 5% of the weights. Coefficient is substantially smaller than, like, essentially half of the 0.07. And the early versus later, it is 14%. This is the coefficient as well. So this is essentially the output of the Baker decomposition. As I said before, if I drop the never treated group from my data and I run the same type of analysis, so I'm just doing the modification here, but only using the never treated, right? I only have two comparisons. This is early versus later. This is a clean comparison. This is the clean diff and diff. And then later versus earlier, it is the forbidden one. And the weights now are much higher. So depending on the specification that I have, like this type of weighted average representation will change. Do this. What about negative weights? Do we have negative weights? We don't have negative weights. Remember, this discussion is related to the proportion of weights attached to the forbidden comparison group, right? And if you do not want to go there, you want to have something that is explicitly about negative weights, you can use the French decomposition. And that's related to this CDA, this 2A fixed effects weights function, who lives inside the 2A fixed effects weights package. And I'm just going to run over here, right? It's going to tell you in the original data set, right? All weights are positive. No weights are negative, which is already, we discussed this in the slides, right? So this is, in this application, there is not enough dynamics and heterogeneity such that negative weights pop up. If I drop the never treated group and run the same analysis again, now I do have negative weights, right? So this is a situation that, again, depending on which kind of comparison group you want to use, the way you structure your data, you may have negative weights or you may not have negative weights. This is a situation you're going to have to decide how to proceed. My personal point of view is that these estimation methods were not built for causal inference, right? They are not built to be variational cautious. I prefer to use difference and difference techniques. They are built to handle heterogeneity from the very beginning. But again, I have a horse in this race, right? So I have written several papers on the topic that leverage this type of variation. And that's, of course, is the view that I take. Now, I have here how to do 2A fixed effects regression in event study. I'm going to have this in a plot, right? Which is essentially this plot here, who I show in the slides, right? So it's a 2A fixed effects plot, which is related to the discussion we had on event study, that is contamination effect, all these negative effects here. I'm going a bit fast here because we are almost out of time. So I want to at least cover the modern tools as well. All this is available to you guys. You can go read this. The code is fairly well documented, right? I try to explain everything that I do, so it should be self-explanatory. Finally, how we can embrace heterogeneity from the very beginning using Callaway and Santana. We're going to use the DID package, and then we're going to use two functions. The ATT function, the ATT-GT function, it is the function that going to provide the building blocks, the ATT-GTs, and the syntax is like this. I'm going to have the outcome of interest, the time identifier, the cross-section identifier, the group identifier, the name. I don't have covariates in the examples. I have weights. And once I do this, right, essentially, I have here a big table of all the possible ATT-GTs, right, depending on the group and time. And because I do not, in this application, we have very few treated units in some of these cohorts, I do not recommend you interpreting these ATT functions by itself. I strongly recommend you to actually do the aggregation step, which is what I have here in line 185. I do this, I have the summary of the aggregation steps here in event study. And this is essentially doing the same thing for a different alternative control group. But we just plot these things here so you can see like the plot. This is one style of the plot. I don't like this very much for this application. This is the other style of the plot, which we have seen in the slides as well. Right. So again, you can look at the R file that I have provided to you. Unfortunately, I do not have time to go line by line because we are very time constrained. But I want you to make sure that, like, with the material we have provided in this 4 hours workshop, we should be at least feel comfortable about the new developments, the limitations, and how you can tackle them. So I'll stop sharing and just do a quick plug to finish these things with, again, if you want to learn more about this, check out our Chaos Solutions website. A lot of material is there, right? And if you have any questions to me, you can contact me by email or on Twitter. I'm very active on Twitter. Feel free to write me on Twitter as well. With that, that's all I have to say. Thank you very much. I'm happy to stick along more to answer some more questions, but I'm not sure if that's feasible.
Yeah, I mean, if people, Paul and I can stay on for a little bit, if people want to hang out and we'll try to go through some of these questions. Like I was saying, Pedro, otherwise we can just grab a document with remaining questions and send that to you so that we can eventually post that on the website with the rest of the materials for the class. But I do want to give you some virtual applause because that was outstanding. I mean, it's your expertise in this area is very clear. So especially with the focus on the modern tools, I think that's incredibly valuable. So hopefully people can make use of those R scripts. So yeah, just to make sure, Paul and Frank, can we let the recording run a little bit longer?
Sure thing.
Okay. All right. Yeah. So let's try to just get through some of these. I mean, it's just people have been
I saw 35 is a lot.
This is like blowing away any record I've ever seen for any Zoom webinar, but okay. So here's one that was asked a little bit earlier. So the statistical literature for observational longitudinal data has now for more than a decade used the paradigm of the underlying randomized trial that an observational study should emulate. There's now published guidance on how to specify the randomized trial that one would do if randomization were possible, and then design the observation analysis to mimic that trial. This paradigm was explained and applied to a typical policy analysis by Ben Michael in a 2021 paper. Yet, except in a few cases, the econometric literature seems to ignore what is called the target trial paradigm. Does the target trial approach solve the problems you discussed with staggered adoption and heterogeneity? And does not the rigor of emulating a hypothetical randomized study represent a global solution to these problems? So there's a lot going on.
So I mean, the answer is yes, it does help a lot on that. I mean, if I get the reference correct of the Ben Michael and co-authors, is the paper with Liz Stewart as well. In fact, the solutions they propose for difference and differences, it is the one based on Calloway and Santana, right? So this is one of the building blocks of like how we move forward. Right. So in general, that's the way to go, because once we have clear the comparison group, the target parameter in your mind, the intervention would have done it, right? You would never run into this problem of negative weights from the very beginning, because this whole idea of like target trials, like we have to be careful with our causal assumptions and our control group. And we want to put the question before the estimation method first. We don't marry a method, we marry a question. Right. Once we put the question at the spotlight, the estimation method becomes secondary, and that's how you avoid the problems, right, of this literature. I agree 100% that the econometrics literature historically have focused more on the estimation method than the causal question, and that's where everything starts to go south, right? I think the way I see this literature on difference and differences, like kind of like, well, let's move things back from questions then methods, and that's almost all solutions boils down to pursuing that path.
Got it. Okay, thank you. Next one, should it be considered to drop states from a control group that will eventually become controlled, but are not yet available in the data?
So you can do that, right? If you have those information about like, the future treatment time, right, you can leverage that. That is usually important if you want to address anticipation issues, right? Because if I know when they're going to be treated, and I'm worried about anticipation, I can also shift that timeline, like the effective treatment date, right? Because of that. So if you want to use those information, go ahead, use that. It's useful information. I'm all in for leveraging all the information you can come up with, especially focusing on contextual specific knowledge, right? So this, I mean, this has to come and guide everything we're doing it.
Got it. Okay. Does it make sense to have confidence intervals for the weights?
I don't know. I don't think so, right? Because weights are, in general, we don't care much about the weights. Weights are just measure of like nuisance parameters. So what we care is about the target parameter. So that's the way I would actually do it, right? So I don't think, I mean, the weight is just a stepping stone to get into what we want. And say, I'm worried about negative weights. Well, you can avoid all those problems from the very beginning. Just choose a different estimation method. I think that's easier to tackle than to start like to. There's a lot of interest in kind of like resurrect two-way fixed effects methods, right? I get that because we have been using those for so long. That is, people are very reluctant to leave that away. But the new methods are as simple as two-way fixed effects, right? So it's comparison of means at the end of the day.
Yeah.
And in my view, nothing can be simpler than comparison of means. So, but I mean, I'm not the universal proof holder here. So, but that's my path, how I would like to do it.
Cool. Okay. Do false comparisons also happen when we do synthetic control style analyses? So that's where you have a control for all times by construction or by synthesis.
So is synthetic controls with staggered treatment timing is very recent, right? So actually, like Eli Bain-Michael, Jeff Rothstein, and Avi Feller has 2 fantastic papers tackling these issues, right? And they kind of like avoid these negative weights by construction because that literature kind of like follows the literature in diff and diff, so they can bypass these issues from the very beginning.
Okay.
So the general answer is like classical methods for synthetic control did not allow for variation treatment timing. Only recently they have allowed, and once they allowed, they are already aware of these problems, so they bypass this from the very beginning.
Got it. Okay. Would it be fair to say that if we're able to directly measure the treatment effect for each group, then why do we care about averaging? Why not just report the vector of treatment effects directly, or why not average them using, say, the population's shares for each group as weights, which I think you touched on obviously later in the
100%, yeah. I mean, if you have enough data, report each group one by one. That's the best case scenario. The issue becomes complicated when I have several groups and I'm concerned about statistical power. That's when aggregation comes into play, like for statistical power reasons, or about summary, because I mean, I cannot go to a policymaker and give them 20 plots. They're gonna say, what do I do with that?
Right.
So summarizing the facts in that word is helpful, both for communication. But yeah, if you the ATTGT is, if I can plot them all, that's the best case scenario.
Yep, great point. Okay. Thank you for the great presentation. How would these methods work when you have intensity over time as treatment rather than on-off treatment indicator over time? Would the results that you've discussed hold in that case as well?
So yeah, that's the case when I have like variation, the treatment is continuous, right? Continuous treatment, it's a much more complicated beast. Everything that I have talked today remains and new problems appears, right? Because with continuous treatment, you have to be careful about with binary treatment, the building block is easy. It's always like dosage, group G versus not, is treated versus untreated. When you care about continuous, it's like what is the causal effect of interest? Is a marginal increment of the dosage, or is it going from 0 dosage to dosage like S? So those create additional problems. We are currently working with Brent Colloway and Andrew Woodman-Bacon on tackling this problem with staggered adoption and all that. So a new version of our paper is about to come out in 2 months, I hope. But yeah, everything we talked today, the problems persist and new problems appears. Even in the subperiod case, there's a lot of like interesting stuff going on. Even in the simple subperiods case, we have a lot of work to do in that situation.
Yeah, no, that's clearly an interesting area. Okay. And Pedro, again, feel free when you're tired, we can stop. So we're just trying to get through these. in the case that pre-trends hold for the overall sample, but not for a subgroup, does that mean we have a bad control, or does this indicate that there are compositional changes in the repeated cross-sectional data?
Very often when that I mean, that's a kind of knife edge case, like that I can have violations for subgroups, but then once I average, the violations get off, right? I mean, this is, if you only care about the overall effect for the entire sample, I mean, go ahead for that, right? This essentially like our assumption is going to hold for the overall. We're not going to be violated for subsample analysis. This is going to put some kind of yellow flags on heterogeneity analysis, for example. So, but I mean, mathematically it's possible, right? The arguments to justify is just like slightly trickier. So many empirical researchers are going to be very uncomfortable in those situations.
Yeah. Okay. What happens when we add unit-specific time trends to the event study specification? So kind of like a random coefficients question.
So that's a great question, right? Because in my view, once you do that, we step outside differences and differences because you're not rely on parallel trends anymore.
Mm-hmm.
But I have strong views on what's the difference and difference and what is not. Perhaps I'm the one who have the strongest view about those things than everybody else. But in practice, very many people incorporate unit-specific effects that in general change the analysis. I mean, it's more general because it allows for like violation of parallel trends. On the other hand, that also incorporates, you essentially have to model the unit-specific trends in a parametric fashion. So it strengthens the assumptions one direction, relaxes in another. My overall view is that that is outside diff and diff. If you're worried about violation of parallel trends, go do the sensitivity analysis of Rambachan and Roth, right? There is code available online. In the bonus track of the slides, I have slides discussing those cases, and that's an alternative to instead of using these random coefficient trends, and I think that's better. But I mean, again, your taste.
Yep. Okay. If you're worried about anticipation, can you still push treatment date back in an event study, or will this introduce potential heterogeneity and dynamics based on when the units anticipate?
So if you're worried about anticipation and so suppose I'm worried about anticipation in 5 periods, right? So in everything in the ATT-GTs, when I'm recovering that, I use the G-1 time period as the reference group. If I worry about not anticipation violations, right, what I have to do is I have to go more back in time before the period. So instead of going G-1, I'm going to go G-1 minus K, and K is the number of periods that I have to anticipate. That's going to change your ATT-GTs, and then I can aggregate them to have a reliable event study coefficient, exactly like everything else goes on.
Got it. Okay. I use Poisson two-way fixed effects model in a paper, and I'm not sure there's a simple solution for count data yet. Do you have any suggestions? This individual estimated the TWFEs separately by treatment group based on year of treatment, but that obviously leads to a small cluster problem.
So that's a great question, right? So Jeff Woodrich has a paper on that is like, I think it's going around, in which he tackles how to do differences with like nonlinear link functions. Of course, the parallel trend assumption changes. It's not a parallel trend anymore. It's kind of like in this Poisson model, it's going to be a ratios in ratios. The good news is that the coefficient that came out of that, if you do not have variation treatment timing, things work very well. Okay. With variation treatment timing, you can adopt the same kind of subsample tricks we have done here, but instead of doing the OLS two-fix effect, you do Poisson two-fix effects within each of these 2x2, and you aggregate. I'm not sure if Jeff's covered that case or not in his paper, but it's a natural next step to do that.
Okay. Just to make sure I understand this correctly, the issue about negative weights in event study causes the estimated ATE to move away from the true effects?
Yes, that's true.
That's the big issue. Okay, that's just yes, no. Okay. Does event study via two-way fixed effect specification assume that treatment stays on after the treatment period?
Yes, that's the one that I'm building on. Yes.
Okay, got it. That's yes, no. In general, what are the statistical ways to test parallel trends beyond visual inspection? I think that was in your bonus slides.
Yes, so then you can do, I mean, it's kind of like you're going to do some kind of sensitivity analysis.
Mhm.
And the main idea is like, for example, I can look at pre-trends, right? And I want to leverage what happens in the past. So let's look at the biggest violation of parallel trends in the past, how far away I am from zero in the pre-event study coefficients. And I'm going to look that as my benchmark. Then I'm going to extrapolate that linearly. So that's going to be the slope of my violations. And then I can scale this up and down to answer a question like, well, if I have violation parallel trends in the future that is as bad as I had in the past, do my answer survive? Does my causal effect survive to that? Yes or no? Then you can have bounds. And that, I mean, I like that work a lot.
Okay. What happens if in my treatment group, there are only a few units? Like if my sample is 100 and my treated group is only 10 units and I have time variance in the treatment variables. So like a really small sample case with time varying treatment.
So in that situation, I mean, the classical tools, like not going to be, I mean, unless you make a strong like distribution assumptions, classical inference tools not going to be valid, right? So you're going to have to kind of marry some of these modern different diff techniques with inferential tools that are built for two-way fixed effects regression. I haven't seen that done yet, which is again like it speaks to the language. There's so much more to be done in diff and diff that we're just starting to realize. So these are like interesting topics for future research.
Interesting. Okay. Is the CS procedure, I'm assuming that's referring to CS-DID, is the CS-DID procedure taking into account unit fixed effects? And in CS-DID is IVAR the panel identifier, but what exactly is that doing?
Yes, so essentially, yes, we automatically account for unit fixed effects. So you don't incorporate fixed effects as a covariate no matter what. That's a no-no, like this is a big red flag.
Right.
I mean, so essentially, once we start specialize the unit fixed effects, or the cross-section identifier from the panel, we're gonna use that thing to keep down like the influence functions. So to do inference, like we're gonna keep that observation valid, and also gonna be able to take differences, like short differences, long differences, based on that. So we account for unit fixed effects built in. Do not add unit fixed effects as a covariate in your specification.
Yep, exactly. Okay, good. Just to clarify, I can use both the not yet treated and the never treated in the same analysis?
You can, yes. I have seen it happen a lot, like you use separately both, right? Just because sometimes the results do not change. And when they change, it's like some food for thought why they're changing. Like, is my identification strategy fragile? It fosters more discussion, and this is a thing that is positive because we have to start better understanding selection mechanisms that justify parallel trends.
Got it. Okay. And just as a general note, I want to ask people to stop typing questions because we don't want to abuse Pedro's time. So if we could halt on the questions for now, we'll try to get through these. We appreciate all the interest. So in this dynamic period weighting, the group in the middle of the data set will tend to get the largest weight. Not sure what that means exactly.
So can you repeat the question?
Yeah, it said in this dynamic period weighting, the group in the middle of the data set will get the largest weight.
That is only true in the two-way fixed effects regression.
Okay.
Right. So in the Callaway and Santana aggregation scheme, that's not true. The group who has more units is going to have more weights.
Got it. Okay. Okay. Can you give us an example of a weight that's proportional to a size? So, and then he used an expression which is going to be kind of tedious to read, but
yeah. No, my feeling is that like weights that are proportional to size is like it's just the number of observations in a given group.
Right, like in a cluster.
Right. So yes, in a cluster. So that's the kind of the weighting scheme we are using it.
Yep.
So
Okay.
NG divided by N, and N is the total group. NG is the number of treated units in that given cohort. That's actually how we're estimating it.
Okay. How is the interpretation of the aggregated coefficient of the event study, the CS method, is it relative to the average of all the pre-periods?
No, it is not. Each coefficient is going to measure the average treatment effect at one period. So when E is equal to 0, it is the average treatment effect among treated units who have been exposed to treatment for the first time, and that's an overall average, right? So that is, I mean, in the computation, the comparison here is in the absence of treatment, right? So we are not measuring things relative to any point in time in the past. We are using the point in the past to pin down the levels, right? To impute the untreated potential outcome. So everything is the ATT is like treated versus untreated. Then the event coefficient is going to say like, oh, how many periods have passed since treatment has started? That's going to give you these interpretations.
Okay. Next one says, assuming there are many treated and untreated units, how should we make sure that PT holds, parallel trends holds in each of these 2x2 ATTs? Should we judge based on pre-trends, or can this method, the CS method, combined with synthetic control or synthetic difference and differences be used?
So in general, the more groups you have, the more time periods you have, the harder the assumptions to hold, right? That's the truth. Like I have more groups, more time periods, the assumption is gonna like pile up more. So it's possible, again, like to have violations of parallel trends for this group and times, such that the violations cancel out each other in the aggregation. I'm not telling that this is the way to go. I'm telling this is mathematically possible, right? Because it's testing parallel trends everywhere. It's possible. I mean, you can test that. Actually, we have a test of that built in the package, right? But usually these tests are yes or no. It's like, I don't like the yes or no, because it's how much also matters, right? So then once you aggregate, the how much can be better quantified than the violations in one cohort versus another.
Yeah. Okay, from the recent example, why was the estimate not 0 at event time 0?
Oh, that's a great question. This is the question we get the most, right? I mean, we get this question so often that we actually we add additional features in our package. So the reason is that ATTs are well defined for the future, from 0 onward. In the past, right, we have to we have two options. We either like fix the estimand and extrapolate back to the past, which in that case, we're going to use the universal like reference group, which is going to be G-1, right? In that case, it's going to be normalized. That's one option. The other option is that at time periods -1, I can compare -1 versus -2, right? I can do short differences in the past as well. Essentially, the linear combinations, the assumption that are under parallel pre and post trends, all these are equivalent. Okay. In my view, doing this rolling comparison group, it is more useful to detect violation of anticipation assumptions, but it's less useful to detect violations of parallel trends. We have a blog post going deep discussing this at Brent's webpage, because I must have answered this question at least 100 times by now. So okay. Yes, many people are confused by that. We made the choice early on, we stick to that, but now we also allow for the other ones.
Okay, got it. Cool. All right, yeah, I'll have to check out that blog post. Okay, so we are supposed to run separate analyses between treated versus never treated and treated versus not yet treated, or can we just run the whole data set together and get the pairwise comparisons? I think you've already kind of answered that. So
yeah, you can run the whole thing together. I mean, it depends on the level of aggregation details that you care. Right, but I mean, there is no point of doing separately if you only care about the aggregate answer. Okay.
CS did estimates an overall ATT and a post-treatment average ATT, which is preferable to report as the primary estimate of interest.
The answer is I don't know, right? They have different aggregation schemes. The default we have, it is the cohort average, right? But they tend to be very similar, right? It's very not, if you want to report an event study plot, the average of all post-treatment event study is the most natural comparison, right? So I would say if you're going to have an event study, average the post-treatment event study coefficients. That's the natural like aggregate parameter.
Got it. Okay. Are there examples or recommended papers that apply the latest DID techniques that you were talking about in contexts that don't involve across-state comparisons? So is anything?
I have to search. I don't know. I mean, I'm pretty sure they are. I just have to search.
Yeah, probably just a Google Scholar search might
Yeah.
reveal some of those. Okay. When creating groups based on the year in which it was first treated, the sample size is reduced, and this can cause the confidence intervals to be large. What should be done in these cases?
Then you're gonna have to deal with the aggregation. I mean, so there is no magic, right? So
Right.
if you embrace heterogeneity, and there is a lot of heterogeneity, right? I mean, the variation is limited, right? So in the aggregation step, the confidence intervals tend to be tighter. The ATTGT is gonna be wide because you have that. I mean, essentially it's telling I don't have power to detect like small deviations,
Mhm.
or I lose precision. Once you glue things together in the aggregation steps, that should resolve it. If you still want to have the ATTGTs and have tighter confidence intervals, you have to add additional restrictions on heterogeneity to leverage those.
Okay. Okay. Just a few more here. So previously the balance test using the covariates as outcomes in the TWFE model were standard. What is the expectation now to demonstrate balance?
Well, can you repeat it?
Yeah, so like testing for balance between groups in terms of covariates, balance test using the covariates as outcomes in the TWFE model were standard before. What would be the expectation now for demonstrating that kind of balance? Or maybe it's the same.
I mean, you can do exactly the same. Just
Yeah.
replace the outcome like for time varying covariates on the
Yeah.
left hand side and do different. I mean, and do CSDID, do one of this Slan Abraham with that outcome on the left hand side and report exactly the same.
Okay. Can a technique like this work if you collect treatment and control data in slightly different periods? For example, control data in periods 1 through 5 and 11 through 15, and then treatment data in periods 5 through 10 and 15 through 20. So for instance, you're accounting for time varying covariates and you have equal intervals between time points.
Diff is not designed to take those designs. I mean,
Yeah.
it may work if you make additional assumptions, right? So, I don't know, like shift time, like, I mean, only what, I don't know. In general, the answer is no, right? And perhaps you can do something about it to switch, but not off the shelf.
Got it. Okay. Can the Callaway and Santana method be used when the same unit is treated in different time periods?
In general, no, it's not designed to do that,
Hmm.
right? I mean, there are some hacks you can do it,
Mhm.
but the estimation method is not designed to do that.
Okay, got it. The CSDID work with repeated cross sections.
Yes, it does. It is lower,
Yeah.
right? But because the memory allocation is trickier, but it does work.
Okay. Is there a minimum requirement for the number of observations within each group, like a rule of thumb or something like that?
So depends if you care about the ATTGTs or the aggregation. We
Hmm.
have done simulations that if you have 10 units for each group, right? And you care about the aggregation and you have, I don't know, like 10 of those groups, things that works reasonably well. But again, it's always simulations.
Yeah, it's
right,
all
I mean-
simulation. Mhm.
Yeah.
Okay. In CSDID, which aggregation option corresponds to the average effect of participating in the treatment for the group of units that have been exposed to the treatment for exactly E time periods? Is it ag event?
Dynamic.
Dynamic.
Dynamics.
Okay.
Yes.
Okay, so the dynamic is the option. Okay, thank you. When taking the not yet treated units for the control group, the last units to receive treatment have very few controls. Is that a problem?
It is the best you can do, right? So, I mean, that's part of the method. In general, this means that, like, I mean, long run effects are going to be very hard to identify.
Yeah,
Unless the effects are huge, you're going to lose precision over there.
right. Can CSDID be used for continuous treatments?
No.
Like a percentage, so that's not possible, yeah, okay. Okay, 3 more. Could a difference in difference analysis be used when the observations are different locations and measures are collected daily pre and post treatment?
I think yes. I mean, I don't understand the question, but I mean, if you have a time index, which is day, and you have which are locations,
Right.
you should be able to run this. But
Right.
you need to have like locations, like a cross-section identifier and a time identifier, and you need to have like a unit who at least is encrypted in some periods. And
Yeah.
units, I mean, and this is like locations that are treated. So we have to have variation in treatment status between locations.
Okay. Hopefully not a silly question, but if we want to report the effective number of observations underlying the CS-DID regression commands, how can we do that? See, I use the never treated and I want to aggregate. Do I just add up all the observations of the separate 2x2 DIDs?
Yes, you just go and look for deployers, data manipulations, and do this outside the package.
Outside the package. Okay, got that. Okay, final question. Can you compare your method of averaging ATTs with the quote unquote stacked difference in differences models that some papers have used in the literature? How do those compare?
Yes, we can. I mean, in general, let's put it this way. The methods are different. So stack regressions, stack diff and diff going to avoid negative weights by construction, right? If you do not play with weights within the stacks, it's going to recover a various weighted average of the effects. So the weights are different. There is a lot of this discussion in the paper by Gardner, right? Who discussed like the implicit weights in the stack regression, which is a great paper, by the way. And I mean, so in general, it's different. If you're very good at regression, right, you can undo these weights such that the weights match each other, right? So there is a way to match each of these things together, but you have to be like fully aware how to do that. I'm very bad at data manipulation, so I don't do that.
Okay. Okay, well, 145 questions. That is something
We did it.
else. Like
Yes.
I said, that's just blows away any other standard that we've ever had. So Pedro, thank you so much. This was an outstanding set of information, outstanding presentation. For folks who are still online, again, you'll be receiving a feedback form, and Paul posted links in the chat to fill out that feedback form. So we would definitely welcome that feedback. Materials will be posted. The recording will be posted soon, so stay tuned for that to the ISR YouTube page. And again, just kind of a virtual round of applause for a warrior of an effort getting through all this material in just 4.5 hours. So Pedro, we thank you again, and good luck with the rest of your causal solutions work. That's fantastic. So, but we really appreciate all the time you spent today, and hopefully everybody got a lot out of this. So
thank you, Brady. Thank you,
Okay.
Paul. Thanks everybody for sticking together for the
Yeah.
marathon of 4.5 hours. And I mean, you know how to find me. Thanks
Yeah.
everybody. Appreciate it.
Yeah. Okay. Thank you again. So Paul and Frank, let's just stay on for a bit. Yep.